Hi, I'm Jing from University of Rochester. I will present our work, A Simple Baseline for Weakly Supervised Scene Graph Generation. This work is collaborated with University of Wisconsin-Madison and Adobe Research. Given an image input, the scene graph generation task is to output all the objects' categories and locations, as well as their relationships between the objects. So the scene graph is a symbolic graph abstraction of complex scene, and it can enable various downstream tasks such as VQA and image captioning. However, the current scene graph is mainly trained on visual genome dataset in a supervised way, so it requires laborious annotation, and the model is confined by the limited object and the relation categories, so the generalizability of the model is poor for the out-of-domain images. On the other hand, a large amount of image and text pair in the web, such as conceptual captions. Another idea is to directly learn the graph structure from the image and caption pair. However, the challenge is that how does the graph structure emerge from the image and caption pair? Here is one training pipeline for language-supervised scene graph generation. Given an input image, we get the region proposals. And given a caption, we use language parser to get the subject, object, and the relation triplet. And then we input the region proposals and those relation triplets to the Weakly-Supervised SGG model. So it is important to research on the Weakly-Supervised SGG task. The training pair consists of an image and an ungrounded scene graph, where no correspondence between the object location and the graph node. And in the test time, given an image, it will output the full scene graph. Well, we propose a new framework that decomposes the task into a weakly supervised graph matching part and a supervised scene graph generation part. During training, both label graph and visual graph go through the graph embedding function F to get the node feature. Then the similarity matrix is computed for each pair of visual and label nodes. Then Hungarian algorithm is used for the graph matching to get its best match. In order to train the embedding function, a contrastive learning is used to pull together the matched nodes and push away the unmatched nodes. And the matched label graph is used as a pseudo-label to train a standard SGG model in a supervised way. To train the graph matching part, the triplet loss is adopted. And to train the standard SGG model, we can use any supervised SGG model such as IMP and motifs. Here is the matrix. The pred class is given object location and category, output the relation category. The SG class is given object proposal, output object category and the relation category. And the SG gen is given an input, output the whole scene graph. First, we evaluate the graph matching performance. For each of the aforementioned settings, we define 3 recall. Our object only counts the box that matched with the correct category. Our instance counts the box matched with the correct instance, which means it needs to match both the object category and the correct neighboring context. And our predicate counts the correct matched relation triplet. Our proposed weakly supervised graph matching method is much better than the VSPNet according to the graph matching performance, and the upper bound indicates the best we can match given object proposals. For the evaluation of the scene graph generation, we adapt different supervised SGG model, IMP, motif, and EMP. Our proposed method is much better than the VSPNet on all the metrics. Here is the visualization of our detected scene graph. In short, the green are correct and the red are incorrect or missed. Thank you for listening.